Thank you so much, Rak. And yeah, let me begin by apologizing that I can't be there in person. I would have very much liked to be a part of this in conference in person and interact and discuss with all of you. I'm very sorry about this. But yeah, so today I'm going to talk about fantastic beasts and how to find them. So I'll have to tell you what fantastic beasts are, and then I'll have to tell you how to find them. Okay. And this is, yeah. So this is basically based on two papers that we wrote with Evgeny Sobko and Shubhajit Majumdar. And this first paper was 2023, and the second one came out this year. The gap between these two papers essentially represents the time between having a framework that works in principle and then actually getting it to work. Okay, so yeah, before let me begin by an overview of the talk itself, so that like if you find that it's not sufficiently interesting, you can safely decouple, knowing that you have the key results already. I'm going to talk about what is called the Yang-Baxter equation, and in a sense, this is the defining uh, this is in a sense a defining property of quantum integrability, and this involves essentially d to the 6 cubic equations in d to the 4 functions, where d is some parameter, which could be 2 or 3 or 4. I'm going to talk about what that is. But you can see that this is highly overdetermined. These are functional equations. So you have way more equations than you have variables. So generically, you would expect there are no solutions at all. What makes nonetheless, there are solutions, and not only are there solutions, they're also extremely important to theoretical physics in general, condensed matter or string theory or what have you, which is why one can call them fantastic beasts, because they have no right to exist, but yet they do, and they have these marvelous properties. Okay, so and typically, of course, like you might imagine that as the number of variables grows very large, they are so you might wish to try and solve them algorithmically, and that becomes quickly unfeasible. And what I'm going to do is I'm going to show you how and why deep learning can be used to provide candidate numerical solutions, and then we'll try to engineer these into analytical solutions. Okay, get rid of this. Okay, so let's begin by describing what is quantum integrability. And here's one simple-minded definition, with apologies to the experts in the audience. So imagine that there is a site, there's a spin chain of n sites, and it's periodically identified. So it's like a circuit, and then every so many steps, there's a little site, and there are n such sites. Okay, and what you can think of is that there's some particle that is hopping from one side to another, and at each site there is a degree, there's a vector space that describes the degrees of freedom on that site. Okay, and what we're going to assume is that each of those vector spaces is isomorphic to CD, which is the d-dimensional complex space. Okay. Further, I mean, this is a further simplifying assumption that we are going to assume only nearest neighbor interactions. So if you're sitting on one site, you can only interact with your neighbors either to your left or to your right, but you cannot see more than one step beyond. Okay. And these interactions are, of course, encoded in what is called the Hamiltonian, which you can think of abstractly as an operator that takes you from this tensor space Vk times Vk plus 1 to another state in that same vector space. Okay. And so, of course, this is just any generic Hamiltonian. And what we mean by quantum integrability, and this is where I apologize is even more to the experts, is that there is an infinite tower of conserved charges Qn. Okay. And these are conserved in the sense that they all commute with the Hamiltonian. Now, if this Vk vector space is d-dimensional, then Vk times Vk plus 1 is d square dimensional. And therefore, the Hamiltonian is d square times d square. And what this means is that these d square times d square entries of the Hamiltonian are extremely tightly constrained because they must obey all of these infinite number of constraints, right? And which is another way of seeing why there shouldn't be any, I mean, naively, if you'd imagine, there aren't any such solutions, right? Um, so, except trivialities. So let me tell you about one way of constructing these solutions, uh, which is that you define what is called an R matrix. And this is a set of functions, d square times d square, so d to the 4 functions, which obeys a particular equation over V1 tensor V2 tensor V3. And that is this equation. Now, the structure of this equation is not super important at the level of our discussion. What is important is that these are polynomial equations, and these are, so this is valued over d to the 3 squared, so d to the 6. So this, these are the d to the 6 cubic equations, and these are the d to the 4 variables, okay? And then what we further say is that the conserved charges are encoded in derivatives of R, okay? And again, like this is where I, again, beg the experts for mercy. But what is true is that at least the Hamiltonian is given by this object, okay? So you go to R is equal, you take the derivative at R is equal to 0, you pre-multiply by the inverse of R, and then that is the Hamiltonian which governs these interactions. And essentially, a Hamiltonian is said to be quantum integrable if such an R exists. Okay, so an R that obeys, an R that obeys this Yang-Baxter equation, okay, and obeys this derivative equation. Okay, and you might imagine that, you know, it's very difficult to find any such solutions, and ideally none should exist. But in fact, it's a very non-trivial fact, which goes back to the days of, say, Heisenberg and Bethe, that not only do these solutions exist, there are, in fact, families of solutions that are essentially characterized by algebraic constraints among the entries of the Hamiltonian. So let me show you one of the earliest examples of quantum integrable models, which is called the XYZ model. And the Hamiltonian depends on these three parameters. Yeah, so the Hamiltonian depends on these two parameters, eta and m, and takes this form. So you see that although you have all of these entries turned on, they are all essentially controlled by two parameters. The other thing that you see is that Jx plus Jy is equal to 2. So this is, in a sense, some simple algebraic constraint among the two, within the parameters of the Hamiltonian. Now, of course, this is a linear, so this is almost a triviality. Okay. And the final thing to note is that the R matrix is extremely complicated. So this kind of illustrates all of the difficulties in the problem, that the problem is highly overconstrained. It's the solutions are extremely secretly hidden away, and in principle could be very hard to find. Okay. And now, so here's the central question of the talk, which is that if you take the Yang-Baxter equation as some sort of a defining equation of quantum integrability, then can you explore its solution space to find to obtain new integrable systems? Okay, and there was work done by this done on this by Hitarinta in the 1990s, where he was looking at constant solutions, so not where the entries of the R matrix are not functions but constants. And more recently by Marius Deleuze and Anton Tribitok and collaborators, where they were looking at the kind of R matrices that we are looking at. And in fact, some elements of their construction play a key role in our analysis as well. Okay, so at least in principle, this is well, I don't want to say well posed, but it is a problem. You could take this equation and this constraint, and then just start algorithmically trying to look for solutions. Okay. Now, as I've mentioned before, there are practical difficulties in this. Otherwise, of course, the whole problem would be solved. So if your Hilbert space is d-dimensional, your R matrix is d squared times d squared dimensional. So this is the parameter counting we did earlier. And your Yang-Baxter equation is d to the 6 dimensions. It has d to the 6 equations. Okay. And what that means is that if you have a two-dimensional vector space, such as a spin-half particle hopping on the lattice, then you have 16 variables and 64 equations. But by the time you get to a four-dimensional vector space, you have 256 variables and 4,000 equations. Yeah. So you can see that not only is it highly over-constrained, it becomes more and more constrained as you increase the number of dimensions. And then it's very hard to solve this system of equations using some kind of an algorithm. Another possibility is that you could try some kind of a numerical search, but by giving an ansatz function and then tuning the parameters of the ansatz to solve the Yang-Baxter equation. That may not give you all the solutions, but it will give you some new subset. But then what is the ansatz, right? And this is where AI enters the picture. So if there are any questions, please, I should have said this, please feel free to stop and ask. But yeah, so this is the setup of the problem. The difficulty is, so the setup is that we are looking to solve this set of equations, which is naively highly overdetermined. There shouldn't be any solutions, yet we know that there are, and in fact, it's a very active area of research to find them. And so despite all of these reasons why they shouldn't exist, they do exist. They're extremely important. And what we're going to do is try to use AI or neural networks to solve these equations. Okay. So yeah, that's what I said, that essentially, if your question is that what is the ansatz? Well, one answer is that neural networks are the ansatz. And again, so apologies to a different set of experts in the audience, maybe not the joint set, but and definitely apologies to the machine learning experts. But I'm going to tell you about, or try and recap what a neural network is. So if you want to have a picture of what a neural network is, then you could start with trying to understand what a single neuron is. And for that, you could try and take inspiration from biology. And at least the intuitive picture that we all studied in school is that you have this cell which takes a bunch of inputs, and then depending on what the inputs are, it fires an output. And the simplest model is whether it keeps receiving inputs and fires when some condition is reached. Okay. So if you want to axiomatize that into a mathematical framework, here's a particularly simple object. So you have some inputs being received. These are the xi's, and you compute this affine weighted sum. Okay, so this is w dot x plus b. This is the standard dot product. Okay, and then so you compute this affine sum, and then depending on the value, on whether the value of the sum is positive or negative, the neuron will fire or not. Okay. So this is so this f, which decides whether the neuron fires or not, is what is called the activation function. And this is, of course, somewhat of an extreme example, but nonetheless, at least for having a picture in our minds, it's useful. And if you have that, if you allow me one such neuron, then why don't we equally well have k such neurons? So all of these k neurons take the input, produce this affine weighted sum, and then we act on those sums. This should be zk, sorry, and produce an output. So there are k different neurons acting on the same inputs, and they produce k different outputs, which depend on these parameters. But right now they are unfixed, right? And depending on what these parameters are, the neurons fire or not. Okay. And since hindsight is 2020, let's do another thing, which is that we will call xk, which is the input, the 0th layer of neurons. So we'll put little superscripts on that on our variable so that xk is ak0. Zk is the z's for layer 1, so these are zk1, and AK is what we were calling AKs here, are the activations of the first layer. Okay. And then you can, so it's pretty obvious, you call it AK1. And then you could say that, well, if I'm doing it once, I can do it 1,000 times if I wish. So what we do is that we have this kind of iterative structure where the activations of the previous layer are fed into the next layer and then processed with this nonlinearity and affine weighted sum to produce new activations. Okay, so if you look at L is equal to 1, then you will see that this is just 1 and this is 0, and this is what you were looking at earlier. And what that means in figures is that you have this what is called an input layer, and then you have these series of hidden layers, and then finally you collect an output. At some point you have to stop and you collect an output. Okay, the output function is essentially a tunable function for a fixed x, and you can tune it by changing what w and b are. So this is essentially the simplest object, which is called a multi-layer perceptron. Right. So yeah, this is in a sense the simplest neural network and the one that we'll be working with. Okay. And you might say that, well, okay, all of this is fine, and maybe it's useful for machine learning or what have you, but then what does this have to do with the Yang-Baxter equation? Okay. And then, so the answer to this question, it has several facets, and let me try and, they are somewhat related, but let me try and disentangle them a bit, and hopefully you can spot the interrelations on your own. Right. So the first facet is this idea called called function approximation, and this rests on essentially two claims. The first claim is that neural networks can approximate any function. So this comes with some scare quotes. And the second claim is that not only can they do this in principle, they can also do it efficiently, which means that they're not going to memorize functions. So that's very important for us because we really want somehow for our system to be able to learn what the solutions are, right? So of course, in all of these things like approximate any and efficiently, not by memorization. So these all have appropriate scare quotes, and in a sense, these are all weasel words. But I'll try and unpack them, and then you can see how they're weasel words. Okay. So let's take a toy example, and hopefully we would have studied in analysis class in university, that if you have this function, which is this, so if you consider, say, a univariate function over some finite interval, then you can always construct this kind of a piecewise approximation, right? And by increasing by decreasing the width or increasing the number of pieces, you can come closer and closer and closer to the function. This should not be surprising to anyone. The claim which I'm going to show you is that we can learn or we can construct this stepwise approximation by using neural networks. Okay. And this is, in a sense, a very tiny, it's not even a proof, it's a demonstration in a particular context of this statement, right? Because this kind of piecewise approximation is constructible for at least most sane functions. So the idea is the following. It's very simple. We can use the step function to build the piecewise approximation. And the way you do that is that you look at two of these neurons which fire with the step function. So you have one neuron which fires at this point and another neuron that fires at this point, and then you take the difference of the two. So if you take the difference of the two, then you get a function that is one only between this within this range, right? Because so this is the range where this is one, where the first neuron is fired, the second neuron has yet to fire. And after this point, they cancel each other off. Okay. Now that you have this height, this little height of this little step of height 1, then you can multiply it by whatever you want. Right? And then essentially what that gives you is one such tiny little height. Now, if you have that, then it's very easy to see that you can just add up all of those little heights, construct your output function, and what that will look like for you is a single hidden layer of neurons, is a single layer of neurons. Okay. So essentially just this first layer, and then you add up everything to take the output. Okay. So at least this, it's not really how you would construct the neural network approximator, but it's at least a proof of concept that such a thing in principle is possible. Okay. And of course, you might say that, well, this is nothing to do with anything. I mean, this is just memorization, right? Because I could do this without having neural networks. I could just set up a table. I could have tables of my target function values between x1 and x2, x2 and x3, x3 and x4. And at every point, I could say that, well, my target function has this value, right? And that's not learning, that's just memorization. And I could do the same thing just by building a more and more and more complicated table, right? And even in this, the idea of a table is implicit because I'm constructing my neural network in a way that essentially that I'm constructing this table. I have this list of values of the function, and I have a list of when to turn neurons on and off, right? So in effect, it's the same thing, right? And the second thing is that that increasing your precision is inefficient, right? And what do I mean by that? Well, let's imagine we want to learn this set of functions. And this is what is called a sawtooth class of functions. So you have one function which peaks once and falls off once. Okay, so it starts life at 0, peaks in the middle, and dies at 1. Okay. You have a second one which starts life at 0, peaks at 1/4, dies at 0, and then peaks at 3/4, dies at 1. Okay. And then you have something that has 3 peaks, and then something that has 16 peaks. Okay, or 8 peaks, I think. Yeah. 1, 2, 3, 4. Yeah, 8 peaks. So, okay, now imagine that, instead of having, say, instead of having a neuron that learned a step function, you have a neuron that learns an incline function like this. So if you want to learn this, then what you need are 2 neurons. Or if you want to learn this whole thing as one activation, what you need is 1 neuron. But now if I want to learn this, then I have to put in 2 neurons, one for memorizing this peak, the other one for memorizing this one. And then if I have 4 peaks, then similarly, I need to add more and more neurons. Right? So that is what we mean by memorization. And it means that every time I add a peak, I have to add more neurons in a very inefficient way. But imagine that instead of constructing, instead of adding neurons in parallel, I try to compose functions. So for example, I think of G2 as G1 of G1 of X. So that means that, I have two neurons, each of which are these sawtooths, and then I compose the output. So you can clearly see that, so from 0 and 1, this guy will go like this, and then I act on it with another neuron. So the output of this is 0 and 1. So again, I'll get another peak here, which is this object. And then over here, I'll get another peak, which is this object. And then you can kind of convince yourselves that essentially, if this is the way the counting goes for width, then for depth, it's much more efficient. Okay. Now, none of this actually justifies my central claim that you can learn functions efficiently. But these are at least some kind of plausibility arguments that tell you why it happens. Okay. And if you take a call back to the MLPs, then indeed you see that you have width and you have depth. Okay. And you need both essentially because you can't. So if you want to do arbitrarily well at approximating some function, you can't keep adding more and more and more neurons. Right? It becomes it becomes very hard to work with just at a practical level. So depth will essentially give you that flexibility that you need, that even with some finite number of neurons, you are actually able to approximate a rich ansatz class. Okay. So here's the summary. So the theory is that neural networks are universal approximators. And what that means essentially, the statement and its implications are they should be read on a case-by-case basis. But usually what it means at the level of this kind of a blanket statement is that given any function on some compact or some finite interval, there's a neural network that exists somewhere which is arbitrarily close to it. It doesn't make any statements about how to find such a neural network, how to construct such a neural network, anything. But it's just a statement of existence. Okay. But nonetheless, it's there, and that's comforting. At a more practical level, what happens is that neural networks span a large function space, and they can also quickly learn hierarchical structures in functions. Okay. And that is what is really helpful. Okay. Now, you might ask that, okay, all of this is fine, but what does this have to do with the Yang-Baxter equation? I mean, okay, this shows us that neural networks could, in principle, approximate, I don't know, exponentials or Jacobi elliptics or sines or whatever, but how do we feed in the Yang-Baxter equation into this object, right? And that kind of goes back to this idea of machine learning that we have, that you have this set of images, some of them are dogs, some of them are cats, and then you train some neural network to distinguish between dogs and cats. Okay. So that's essentially a cartoon level. Again, apologies to the experts. This is a cartoon level overview of the classic machine learning problem of supervised learning, which is that you start with some set of known input-output pairs, and you predict the value of the output given a new input. Okay. And the approach is that you assume this ansatz with some tunable parameters, and this is nothing to do with neural networks. This is just any ansatz that you take. It has some tunable parameters. You define this loss function, and you minimize in W to get the best predictor. This is how, for example, we did least square fitting for straight lines when we were in physics lab in high school. Okay? So essentially, if you pose it this way, the idea is that machine learning, it needs data. Right? Otherwise, what is there to learn? And the question is, where is the data? In a classic supervised learning problem, the data would be the value of these functions in these intervals, right? But this is precisely what we don't have. So let me, and of course, people who are familiar with pins and all would see where this is going. But this question of where is the data, let me try and rephrase that question and ask a slightly better question, or at least a slightly more suitable question, which is where is the ML? And to see that, let's ask why or when are loss functions 0. Now, if you have a loss function which is like this should be an f, sorry, and it's minimized at L is equal to 0, clearly, this can only happen when all of the when the function has perfectly memorized the input-output set of variables and values, right? So, and of course, in practical machine learning, there are huge caveats to actually driving this down to 0, but for the moment, let's forget about that. And essentially, the claim is that if you're trying to minimize this loss function, you're searching for functions that obey these constraints, right? And the loss function is 0 when these constraints are satisfied. So if you allow me that, then if this problem of fitting a straight line through some points is a machine learning problem, then so is this, which is that you take a hyperplane given by some points and you're looking for the locus of points orthogonal to the plane, right? And then you hypothesize that the locus is this, and then the loss function is whatever this is. And in principle, what you have is a standard optimization problem. And of course, to make this whole thing work, what is crucial is the choice of a hypothesis class, which is your hypothesis that the locus of points orthogonal to it is given by this object, right? Now, this is of course crucial, but it can be non-obvious. I mean, no one told us that the set of points orthogonal to this is going to be plane, except maybe Euclid. Okay. So, and this is where the input from deep learning arises. So you have this way of posing an abstract functional problem about functions as a machine learning problem using the loss function, and you don't know the ansatz. But then from this discussion about neural networks, it's at least possible that you don't need to know the ansatz, right? So what you do is that you set up loss functions that will encode what constraints you want your function to satisfy. And then you rely on these universal approximation and learning properties to hope that your neural network will actually converge. Is that fine? So here's the setup. So you consider each scalar function in the R matrix and model it with a neural network, right? And all of these functions are going to be constrained through loss functions. So for example, we are going to require that the Yang-Baxter equation is satisfied, because this is only going to be 0 when this identity in the middle of these brackets is going to be true pointwise, right? Similarly, we can have some constraint requiring what the Hamiltonian is, and so on and so forth. Okay. And then optimizing these loss functions is equivalent to solving the corresponding functional equations. Okay. And for this talk, I'm going to assume that this optimization can be done at will. So I'm not going to worry about exactly how to tune the parameters W and B of each of these neural networks. Also, as an aside, you might be a bit suspicious if you are familiar with the literature that these functions of the R matrix, they're supposed to be holomorphic, and guaranteeing holomorphy or training in the complex plane has always been, essentially Moby Dick. But we have a cute little workaround for it, which is that you train on the real line, but you choose activation functions so that the output function is kind of naturally guaranteed to be holomorphic in the complex plane. Okay, so if so if z is real, so if you act on it with tan h or this kind of an object, then its output is also going to be real, but as viewed as a complex function, it's holomorphic. So that's essentially how it works. So let me see. So we have 10 minutes. Okay. So let me tell you at least a little bit about one experiment, which is inspired by the work of Delio, Anton, and Paul Ryan, which is that we know from their analysis that there exist these kind of integrable models, which are integrable if these two conditions, if either of these two conditions are satisfied. Right? And the aim is to discover these two classes. So what I'm going to do is I'm going to visualize these two classes for you directly for today, at least in the interest of time. So you have these two classes. One is the A1 is equal to A2 class, which lies over here. And the A1 plus A2 is equal to B1 plus B2 class, which lies over here, right? Because, so this is A1 minus A2, this is 0. And this is B1, A1 plus A2, and B1 minus B1 plus B2. So you see that there are these two classes which are essentially orthogonal, which are essentially linear loci defined by these two vanishing conditions, and they have some intersection as well, right? I mean, you could have A1 plus A. So you could have A1 being equal to E2 and B1 being equal to B2, and they'd both lie over here. So that's essentially the crux of this constraint of this training schedule, which is that you try to train essentially to points that are over here, and then navigate away from them and train again to try and recover the whole class. Okay. And that's what happens. So essentially we train to some point which is over here. And this is an experiment because we know that these solutions exist. Okay, so which is why we could kind of demonstrate it so cleanly. So you train so that your neural network is somewhere over here, then you repel away, and then you train back to require that the Yang-Baxter equation is satisfied. And if you repelled away sufficiently well, you might wind up here or you might wind up here, right?
Shailesh,
Yes.
what are the units on the X and Y axes
So
of
these
this?
these are just numbers. I mean, these are these Hamiltonian entries which we're treating as C numbers. So
Okay. The
yeah,
values themselves.
yeah,
Okay.
yeah, yeah. Thanks. Okay. So now, okay, there is really very little time, maybe like 7 minutes or so. So let me just tell you about the D equal to 3 extension where much fewer solutions are known. Okay. And what we'd like to do is somehow use this kind of a framework to find these new solutions. And here is the part where you know that in principle, the method works. You've seen it, but how do you actually get it to work? And the problem is this, that to claim that you have this new quantum integrable system, you must solve the Yang-Baxter equation exactly, right? But neural networks, almost by definition, they yield approximate solutions, which is kind of fair. You get what you pay for. If you're looking for a cheap optimizer, you'll get a cheap solution, right? So how do we go from these kind of approximate solutions to exact solutions, right? And this is not just something very abstract or just something that you need to worry about for aesthetics. It's a genuine puzzle. Say, for example, let's take the simple harmonic oscillator. We know that this is integrable. Now, if you add a small interaction, or if you add a small perturbation with a cubic or quartic term, then not only is this object not integrable, it's chaotic. Right? So this is not just, And yet in the space of Hamiltonians, they're just infinitesimally separated from each other. Right? So this is not just some aesthetic worry. This is a real thing, that to show that this object is integrable, you really have to show that these equations are identically satisfied. Okay. And so here's where our starting point was really helped by this analysis of Marius and all, which is that what they showed is that using the Hamiltonian H, you can also construct the corresponding charge Q3. And then you can require that you can impose this condition to require quantum integrability. Now, this is clearly necessary. There's a conjecture by Reshetikhin that this is also sufficient. And there is some recent work saying that this conjecture is actually proved, but I don't know that much about it right now. Okay. And when you have this Hamiltonian, then you solve for the R matrix using some standard analytics. Okay. So let me show you how this thing works. So you start with so now you have a 9x9 dimensional Hamiltonian. So this looks already much worse than the D equal to 2 case. And you start with this, some general ansatz for H in this case. And you say that, well, let me take an ansatz so that all of these off-diagonal entries, upper triangular entries, are turned on. And then you play the same game. You define all those losses, and you train this object down to some acceptable loss values. And then now that, so you find one particular candidate integrable Hamiltonian, maybe which is integrable. The Reshetikhin loss is about 10 to the minus 3. And then you use that as a starting point to plug this thing into your favorite root solver like Mathematica or whatever, to find a bunch of numerical solutions which are of the order 10 to the minus 8. So now you're really, really sure that not only is it one isolated hallucination of a network, there's really some kind of a locus of integrable Hamiltonian sitting there. Okay. And then you don't stop there. What you do is you try to extract some polynomial relations among the Hamiltonian entries, and quite often you get these kind of linear relations as you expect. And not only do you get these linear relations, then you can plug this back into the Reshetikhin criterion and show that it is identically satisfied. Okay. So the point of getting these solutions to the order 10 to the minus 8 is essentially to see that, you'll get some numerical noise in these coefficients. So this would be like 0.99999 or whatever. And then you kind of realize that, well, if it's 0.99999, it's probably 1. You plug that in, and then you show that this is actually integrable. So if you take this Hamiltonian, then you can show that this is the corresponding R matrix. Okay. And secondly, which is the last thing I'd like to show you, is that not only do you get these simple linear relations, sometimes you get extremely sophisticated relations between between the entries of the Hamiltonian. Okay. So for example, you get this kind of like really bizarre looking thing. You get these kind of entries. It's yeah. So these are clearly very sophisticated algebraic varieties, right? As loci of polynomials in CPN. So, and not only are they sophisticated, they are also distinguished in the sense that they all come from solving one particular set of polynomial equations, which in turn come from a very special property of quantum integrability. So it would be very interesting to try and unpack what the properties of these, what the geometric properties of this object are. So here's where we conclude. So let me just remind you of the things we talked about. The Yang-Baxter equation is very important. It's also overdetermined. What we can, and in general, because of the number of variables, it's very difficult to extract solutions systematically. So what we can do is neural networks to get fast and approximate solutions, but then you get what you pay for, that they're approximate. But the other part of the story is that you can engineer these solutions into analytical solutions. We've already found like several new solutions. I showed you two, but we have like a few hundred new solutions actually. But of course, a lot remains to be done to understand them. And now, of course, we also have the problem that we have so many that we have to try and find some way of understanding them at some broader scale. And there are these obvious extensions of trying to look for non-local variants of Yang-Baxter equation, tetrahedrons, simplex equations, maybe even S matrices in the spirit of Zamolodchikov, things like that. So that's all that I had to say. I hope the work was interesting for you. Thank you for your time.